So I think today's will be the kind of the last class, because by seeing the enthusiasm among your friends, I understand that. I mean, I am also lost my enthusiasm to teach, I must say. Uh, so I will kind of wrap up with whatever stuff that has been done in the last class by Shayantan, and I will give you some problem sets and assignment. I will upload that in this weekend, and there will of course be an end sem that will be similar to that of the mid sem kind of stuff, which will be 2 weeks from now, I think. I mean, I will let you know the exact date. Oh, in fact, has the other courses dates have been fixed for the end sem?
No, sir.
Not yet.
Okay. So can you please, so I think it is up to the students to decide when do you want to have your end sem. Okay, I mean, which date. So I would say that, so there is an end sem week, and that will be the kind of week which is, so the next week is technically the last week of classes, but seeing the enthusiasm among your friends, I think what I will do is that I will just end the course today. And if, of course, if any of you have any questions, doubts, you want us to kind of do some extra classes or cover some extra topics, even if that is not a part of the course, we will be happy to take extra core classes, maybe next week or anytime you want. But as far as this course material goes, today will be kind of the last thing. And of course, there will be the more stuff that will come. There will be the problem sets and all that will be there. Okay. The other thing is that, yeah, so next week would have been the last official classes for this course. The week after that, I think, is the preparation week that has been decided. And the week after that, so it's like 3 weeks from now, is the mid end sem week. So can you guys please consult your friends and other teachers and finalize a kind of a timetable for the exams? Okay, when you want which exams to happen. Okay. Again, this will be a kind of a 3 to 4 hour exam, just like what we had in the mid-sem. Okay. Yeah. Any questions?
Will it be online?
It will be online. There's no chance of having an offline thing. Yeah. There is no, I don't think ISI at this point is prepared to have an offline thing, because anyways, technically West Bengal is still under a certain amount of lockdown. So things are not open. Yeah.
Sir, is it possible to take a lecture on Fibonacci heap? Actually, I didn't understand how Dijkstra's algorithm uses
Sure.
Fibonacci heap to.
Sure, I will do that. We will next week. I will take a. I will let you guys know, and I will take a thing on Fibonacci heaps. Maybe next Tuesday only we can have a class on Fibonacci heaps.
Thank you,
Okay.
sir.
Yeah. Exactly. Again, if you guys are interested, I'll be happy to teach whatever things that you want. Okay. In fact, there are a lot of things that I wanted to cover and I could not cover in this course. For example, what happens after algorithms, basically after whatever we do in the first course of algorithms, what happens there. And I know that some of you are interested. I would happily discuss with you guys either in this part of this, I mean, in next week or in future, whenever it happens. Okay. So in terms of this course material, everything that has been covered so far and what will be covered today will be there in the course material in the end sem. Okay, everything, the problem sets and all that will be given, that has been given and will be given further. I think one more problem set will be uploaded. That will be, of course, there also. And that's about Yeah, and of course the assignments and all. So if you are following this course and if you are putting a slight amount of effort to understand the course material or for do the problem sets and all, it should be not hard at all. I mean, else this course can be very hard. That is something that you might have already understood with your midsem kind of stuff. The midsem also will be kind of handed over before that. I will try to do that. Okay, so any course, any questions? I'm sure there will be a lot of questions from many of you about the end-sem stuff, but anything of that form? Okay, so let me just one second. Do you mind? Hello, am I audible?
Yes, sir.
Is my screen visible?
Yes, sir.
You can see my whiteboard, right?
Yes, sir. We can see.
Okay. Okay, so where were we in the last class or last many classes? Last many classes, one thing that we have been trying to kind of drill into your head is that there are this huge class of problems that we have kind of encountered suddenly, right? We started with things like LP, then we had ILP, then we have things like vertex cover, we have independent set, we have what was introduced in the last class called SAT, as the concept of something called a 3-SAT. There are the concept of cliques. Please stop me if you don't know any one of them. We had this concept of matching. We have the concept of flows, right? And there is quite a lot of these things. You can keep on coming up with various things that has been done, right? Now, are you guys all familiar with all of them?
Yes, sir.
At least any one of you familiar with all of them? Hello?
Yes, sir.
Okay, good. So one thing that we have kept on talking about is that, see, there is this huge class of problems, and we talked about what is called reductions. Okay, we did it using some set of concepts of modeling and so on and so forth, right? So basically what happened? If I have a problem one, let's call this one P1, okay, and a problem 2, and now we are only talking about what is called decision problems, okay? Now, decision problems, the idea is that we can say that, okay, I have given you an input, say phi, and I'm asking, is phi in P1? What does it mean? It means that it's a decision problem, right? So that means, does P1 evaluate to 1 or not? Right. So any of this, so basically I can think of this P1 and P2 both to be things that take some input and output 0, 1. Right? Phi is P1 means that, so this is the definition, it means that P1 of phi equals to 1. Right. Now, if you want to solve this problem, okay, a natural way of doing it is to reduce it to some other problem. So if I want to kind of say, somebody comes up and says, see, I don't know how to solve P1, but I have a nice algorithm for P2. Then what can I do? I can take phi, okay? I can take phi and produce something called, okay, R of phi. So R of phi is the reduction. So I can take phi and I convert it to R of phi. Okay. And under the condition that, so such that phi is in P1, if and only if R of phi is in P2. So that means now I can ask that, okay, I don't know how to solve whether phi is in P1 or not, but I can reduce it or model it into a different way. I can change this phi to R of phi, and I can ask, is R of phi in P2? Right? And if Ri phi is in P2, then I know that it is in P2, and if Ri phi is not in P2, then I know phi is not in P2 because of a P1, sorry, because of the if and only if condition. Right? Now, if this is the case, what happens? Which is the harder problem? Which is the harder problem you can think of? Anybody can say which is the harder problem?
Both are of same hardness, right?
No. Of course not. Both are not the same hardness. I am using P2 to solve P1. So in some sense, I can solve. If I can solve P2, I can solve P1. Okay. So that means
Okay.
P1 is easier than P2.
This is not an onto map, right? Oh, forgot.
No, this is not an onto map.
Yeah, fine.
Okay.
Hmm.
So P1 is easier than P2 because if you solve P2, I'm done with P1, right? Fine. So this basically says that we write it as P1 reduces is less than or equal to P2, which is easier. Is basically the idea to do it. Okay. So this is the notation that was used. Okay, this is a very important notation that is used. Now there is one more thing that I missed, I've not talked about. And that is the fact that whilst this reduction is nice, right? But this reduction might be already too costly, right? I want to solve it quickly. You have given me an algorithm to solve P2 quickly. I have used the input of P1, converted to an R of phi, and managed to use R of phi into P2 and solved my question. But maybe this reduction, this mapping, converting a phi to R of phi might take a lot of time. Right? So usually, but one thing that we can see is that, okay, so if, so maybe I can write it, if the reduction from phi to R of phi is in polytime, then so that means what? I can reduce it in polynomial time. As I told you in the last class, somehow we have a nice liking for the polytime concept. So if P2 can be solved in polynomial time, and I want to solve P1 in polynomial time, all I need to reduce it into polynomial time. So I take a phi and I reduce this whole thing. I produce the R of phi in polynomial time. And once I have done the polynomial time, I can fit that one into P2 and ask this question. That can be done in polynomial time. So polynomial time plus polynomial time is polynomial time. Note that the size can also increase. So maybe this one was n, this could have become size of R phi can become n to the power 100. But again, see, if I have a polynomial in n, okay, or a polynomial in n to the power 100, it's still polynomial. Right? So if you are just interested in the polynomial idea, then I am happy to have a reduction that runs in polynomial time. Okay. So then we say, okay, and this is important here, P1 reduces to P2, but we write it a P over here. Okay, so this is, and this basically means that P1 is polynomially reducible to P2. Now, the fact that you can say that there are P over there does mean that there are other notions of things that can come in, right? In fact, there are exponential time reduction, there are linear time reduction, there are lots and lots and lots of interesting things, times reduction. In fact, nowadays in the world of computer science, particularly this applied computer science, polynomials are not good. You usually do it with linear reduction, but let me not go into that for now. Okay, so any questions about this notion? So let me just give a formal proof. Okay, so P1 is reducible, P times reducible to P2 if there exists a reduction. Okay, the reduction, let's call this one R, from 0, 1 star to 0, 1 star, such that for all phi in 0, 1 star, okay, two things are satisfied. First thing is that phi is in P1 if and only if R of phi is P1, now P2. Okay, then I can reduce it. And number two, okay, fine. Number two is that R is a polytime algorithm. So you know that it's a polytime algorithm, meaning this algorithm of reducing R phi to R taking phi to R phi. This is can be done in polynomial in the size of the input or size of phi. Okay, so this is the definition of reduction, polytime reduction. Okay, so in the all the things that we have done so far, what all things have we done? Can we quickly see what all things that we have done? What all things? I mean, I have also forgotten. Can you guys remind me which all reductions have we done? We have done things like, anybody remembers anything? Matching reduces to flow, right? Flows reduces to
ILP.
ILP. Actually, flows reduces to. Okay, so maybe I should not write it. Matching doesn't reduce to flow. Matching actually, yeah, matching reduces flows. Flows reducing to LP actually. But finding a matching is complicated, more complicated. You remember this one, that it was like whether a matching exists or not, that can be written as a whether a flow exists or not in the integer program, in the integer stuff, right? Doesn't mean that you can recover a matching. For recovering a matching, you need the concept that the solution of the flow is an integer flow. But that was different. But this was one thing that we have done, right? We have we done vertex cover?
Yes, yes.
Vertex cover to what we have done? Somebody, anybody, any other thing that we have done?
The vertex cover to ILP.
Vertex cover to ILP we have done, right? Any other? In the last class, what was done?
SAT or 3
SAT to?
SAT.
SAT to 3 SAT was done.
Yeah.
Is it? And then
3 set to click.
Click was done. Right? Anything else? Anything else was done? Okay, so, but okay, let me write down some more, okay? Actually, what happens is that all of them, okay, this is another beautiful thing you can prove, Okay, so proof. Maybe I can write it as a proof. You have written this one. You can also prove that click reduces to SAT. So that means this is less than SAT. You can also say that ILP reduces to SAT. Not only that, SAT also, by the way, all of them are P. Okay, if you remember, if you look at it carefully, all of them were polynomial time reduction. Okay, that is less than ILP. You also write vertex cover is less than SAT. Is less than vertex cover. Okay, so these are all maybe 1, 2, 3. Okay. So these are called reductions. And do you see a pattern over here? What is happening?
They belong to same class. Same.
Right. So that means all of them here, except for the top ones are different. But here, this one, this one, this one, this one, this one, this, all of them seems to be equally hard in terms of polynomial time. Okay, if one can be done in polynomial time, the other can also be done in polynomial time. Okay, and by the way, all of the, I mean, we had proved that vertex cover is in NP, right? You prove that. Okay, so this is a step, another thing. Prove that if P1 is less than P2 and P2 is in NP, then P1 is also in NP. NP, you remember, NP is the set of all languages for which we can verify the correctness. Right? You can give a witness, a small witness for correctness, and I can check it out. That, oh, yeah, this is correct. Right? So, in some sense, all of these problems, they are kind of looks different from each other. SAT doesn't look like ILP or vertex cover at all in the first place. But in terms of hardness, all of them seem to be equally hard, at least from the point of view of polynomials. Okay, and because we have already seen, or vertex cover is, or an ILP is in NP, so all of them are also in NP. Okay, so not only this, I will give you another proof. Okay, another statement that, see, again, the same kind of stuff. Again, I'm leaving you guys with this statements. Okay, if you should go and try to solve it. If you don't get it, let us know, we will do it. Okay, so if P1 is less than, or if reduces to P2 and P2 is in P, then P1 is in P. Oh, right? So if I have to draw this kind of set of things, okay, this is, say, NP. This is the class of NP. Here is the class of P. Okay, these are all the languages that are in P. These are the things that can be solved in P. So this flow is here, say, LP is here. Okay, fine. Matching is somewhere here, and so on. Now, if I have a problem here, and this problem and this problem are similar, or basically reduces to each other kind of stuff. Okay, so they are complexity wise similar. Okay, so let me call this one P1 and P2, and P1 less than P2 and P2 less than P1, right? For example, say SAT and vertex cover. If any one of them lands up in P, then both of them will land up in P. Correct? So in some sense, this is a collection of problems that are in NP, and if we can prove any one of them to be in P, then I'm done. And that means I will be able to prove this thing. So this set of problems are called NP complete. Okay, NP complete. So what are NP complete problems? So a problem that is equivalent to SAT is called NP complete. What do I mean by equivalent? That means, okay, so problem P, so that means P is less than SAT and SAT is less than P. Okay. Now, why SAT? Okay, and what is the speciality of this NP complete problems? You must have heard this term earlier. This is something that is used all the time. Okay. How many of you have not heard it? No one? Everybody has heard it earlier? So NP complete looks like, okay, it's a, but see, note that this is, I have written SAT here, but you could have replaced SAT with any of them, right? You could have replaced it with click, with vertex cover, with ILP, with vertex cover, any of them. It's the same. Because if a problem is equivalent to SAT, then it is also equivalent to vertex cover. Because I can reduce some problem to SAT and then reduce it to vertex cover, one after another, right? Correct. So, okay, good. So this is the situation. I have an NP complete. And now you are saying that, okay, why have you drawn it here? How do you know that I cannot solve these NP complete problems in P? Okay, honestly speaking, I don't know. Nobody knows. Okay, but in 1972, this is this famous paper of Cook and Levin. I mean, this is not a single author, it's a two author people who wrote it. And what they discovered is that not only this, but for all problem P in NP, no, P is not a very good idea, it's a P1 in NP, you can always reduce P1 to SAT. Now, this is a bizarre statement. Think about it. Among all the problems that are there in NP, so among all the problems for which we can verify correctness, they are all easier than the problem SAT. Right? So in some sense, and SAT is also in NP, right? So that means among the set of problems in NP, SAT is the hardest problem in some sense. Now, this is a mind-blowing result. I mean, nowadays we study it in our algorithms course. I'm not giving you the proof of it, but the proof of it can be found in any algorithms book or automata book. So the proof that happens is not the most clean proof, because to define n. So you have to first define what a P is using the Turing machines. And once you define it using the Turing machines, you can prove this one, this statement. But just imagine, right? Here is a class of all problems, all different problems that are there in the world, in some sense you can think of, okay? That can be verified in polynomial time. And among them, there is the hardest problem. So this is something that what computer scientists have achieved that no mathematics subject has ever managed to achieve. To identify a problem that is harder than all the other problems that we have thought about. Okay, a very general thing. It's not like, oh, give me a problem and I will reduce it. No, you cannot prove it using by saying that, oh, this can be proved by give me a problem and reduce it to SAT. No, this is a statement that has already been proved that any problem for which there is a polytime verifying machine, a machine that can verify the correctness in polynomial time, can be reduced to the problem of SAT. And this is what makes it most interesting. So that means I can define this problem as SAT, a very special problem. Now, every problem that are equivalent to SAT, again, they're equivalent. So that means any problem can be reduced to SAT. That means any problem can also be reduced to Fortescue. That means any problem can also be reduced to ILP. Okay, and what it means is that if P is equals to NP, okay, so if P equals to NP, then SAT is in, then N. So let me put it this way. So if P equals to NP, meaning the set of all problems for which we have a solution, or we have a polytime algorithm to find the solution, is same as the set of all problems for which verifying the correctness of a solution can be done in polynomial time, then of course this element SAT is in NP. So then this is by almost obvious that SAT is in P, right? And on the other hand, because of the Cook-Levin's theorem, any problem in NP is easier than SAT. So SAT is in P implies that for all problems P1 in NP, P1 is in P, which means NP equals to P. So what do I have? That P equals to NP if and only if SAT is in P. Imagine this problem. Okay, just think of it. If somebody has come up to you and told that prove that any problem for which, so this problem, right? Any problem that you can verify the correctness, you can also find the solution. I mean, then you have start thinking that, oh, how do I have to prove it? How can I prove it? What does any problem mean? It's a very hard thing to kind of get your head around it, right? Wrap around it, what's going on. But here I'm not saying any of that. This is basically saying that, okay, prove this problem in P, you're done. Right? So this is the where we stand. So that means we have this nice, I will draw it again. Yeah, let me draw it again. Okay, so there is this huge class of NP. Inside it, there is this class of P, and there is this special problem called SAT, which is outside. I'm not saying it's outside, but we right now don't know whether SAT is inside P or not. Since this question is not yet solved, it is not known. Okay, and not only that, around SAT there is a collection of problems that are as hard as SAT. So SAT is not a special problem as such. I mean, SAT historically came up in the first proof of Cook and Levin, but there was no reason that SAT had to come up. So this is a huge class of problems called NP-complete problems. Okay. Now this is what is the important. So now, if somebody says that, oh, I have a problem which is NP-complete, what does it mean? That means the problem that is NP-complete means it is somewhere here. It is equivalent to SAT. Now, if this problem is in P, or if I can come up with a polytime algorithm, it is same as proving that P SAT has a polytime algorithm, which is same as P equals to NP. So if I can, so if somebody says that a problem, say a language L or a problem L is NP complete, it's like, okay, if I come up with a polytime algorithm, I will prove that P equals to NP. Something that we don't believe to be easy, at least. Okay, we have not found out, we have not been able to prove any of that. And so we are not very sure what to do. So it's like, okay, if somebody says that, oh, L is an NP-complete problem, it kind of says that don't ask me to prove polytime algorithm, or nobody should be even trying to prove polytime algorithm. It is not believed to have polytime algorithm. Okay. So this is the main crux of this beautiful subject. Now, this subject is just, we just scratch the subject here, the layers, surface here a little bit, because lots and lots of questions can be asked. Okay. Are there problems here? Are there problems that are not NP-complete and NP? Yes, there are many problems. For example, primes meaning if I give you a number n and ask you, and a number k, and I ask you, is there a number, is there a prime factor less than k that divides n? Okay. So this problem was not known to be NP-complete and was known to be here. But with time, what happened is that people have managed to work out various stuff here. No, sorry, I have all my nice tricks and all are not working. Forget it. Yeah, so primes were here, and with time, some of the researchers have managed to pull this stuff from there to here. They have managed to prove that primes has a polytime algorithm. Okay, there are problems here. For example, people who are working on cryptography, one of the big problems is factorization. And it is not in NP-complete. Factorization meaning, right? I mean, the same thing, like, is there a, oh, sorry, primes is that if you are given a number n and is it a prime or not. Factorization is that you are given a number n and a k. So what is primes? Let me write it down. Sorry, I made a mistake over there. Okay, so this is the set of all numbers n. Sorry. Yeah, someone say something such that P is a prime. Okay. Sorry.
So can you repeat the last sentence?
The primes. Yeah. So the primes are the set of,
factorization.
yeah, I'm explaining. Primes are the set of all primes, right? So you are given a number and you ask, is a number a prime or not? Right. So the problem is that given a number say Q is Q R prime. Okay, so this is the primes problem. And then there is another form of factorization. It seems to be very similar to this one. Okay, but this is all the numbers P comma K such that P has a factor less than or equal to K. Okay, so what does it mean? That means that is there exists a number M less than or equal to K and M divides P. Okay, maybe, right? So again, here it is that you have been given say Q and K. Question is that is there an integer? Okay, so of course this is bigger than or equal to 2. Is there an integer more than 2 and less than or equal to K such that integer say R, that R divides Q? Okay, so this is a number. Now you can check it out. Okay, I can ask you a few questions. Is factorization in NP? Think about it. Okay. And it turns out and something will happen. Okay. And amazing thing is that what you will realize, okay, so maybe you, let you think about this problem, but let me just tell you that if factorization is in P, then any of these cryptographic protocols based on say RSA cryptography. Now, if people who are not familiar with this, don't worry, but RSA cryptography will fail. Okay, so this is a statement that is everybody knows this statement, every researcher. Because so what is RSA cryptography? It is basically the most common form of cryptography when you are using your credit card to buy some stuff. You are using this thing. Okay, you have a number, the bank has a number, and you kind of, the idea is that nobody can break. The idea is that nobody can hope to break or factorize the problem. They factorize the number that you have, and everything is based on that. Your security of your transaction is based on that. That's called that is the one way of doing it, is this RSA cryptography. But they basically assumes the fact that factorization is not in P. Okay, so there are this very nice set of results that are there. There are lots and lots of results. And if you want to study this picture a bit more over here, then this goes into this field of complexity theory. Okay. We don't have time to go into complexity theory, but let me ask you, okay, so let me, before I say something, let me ask you, any questions so far? Any questions that arise in your now?
Why factorization is not in NP? It can be verified, right?
I have not told you, yes, it is in NP or not in NP.
Oh, okay.
But actually it is not. Let me put it this way also. It is not in NP. How can you verify it? Somebody says that no, there is no factorization, no factor. How will you verify that? So verify that you have to factorize it.
Because the
Right?
prime number is that
No.
prime number is in P, you said.
Yes.
So
yes.
yeah, we can verify that whether this is a prime number or not.
No,
So
maybe it's not a
if
prime number. It's not a prime number. But
Then
it
there is
can
factor.
still. I mean, that number, that factor might be bigger than K. Right? You can say whether a number is prime or not. But factorization says that whether there is a factor less than or equal to K.
No.
Right?
So if the prover
Yeah.
gives us a number, say some number R, he'll
Hmm.
give us, then we'll check whether R is less than or equal to K and R divides P or not.
Yes. So what you are
P1
saying is the opposite actually. Okay, this is called the complement of factorization. Okay, so what is the yes instance here? Yes instance is that you ask someone that actually, okay, let me say, yeah, the way in which I have written it, it is in P. Yeah, sorry. Whatever, the way in which I have told it is in NP. Anyways, yeah, so don't worry about that. Okay, so there is, I don't want to go into the other side of it. There is this,
Actually, can you give
Yeah.
us a simple proof where P is in NP?
but P is in NP.
Yeah.
Okay, so what is P?
P is a set of all numbers which are primes, right?
See, what is NP?
Sorry,
Oh,
sorry, not P. Primes. Primes is in NP.
oh, primes is in P. That's a very hard problem.
No. Primes is in NP, not primes is in
Oh,
P.
it's also very hard.
Okay.
It is also very hard. Okay. Yeah, right. Yeah, actually, primes is in NP is a very hard thing to prove. That's true. Yeah, if somebody says that yes, it is a prime, how will you verify that it is a prime? So maybe I could have asked this question, and that's a more complicated thing to prove. Yeah, sorry, I have not. Yeah. Anyways, let's not go to the primes thing so much because I think that will completely take away your focus from this whole thing. But in terms of the P and P reductions, is this clear? Have you guys tried out some reductions at your home? I'm assuming that the silence means no. So let me put it this way, that there will be lots and lots of reduction in your NSEM. You like it or not. The reason we have spent so much time in this last part of this course on reduction is exactly because of this. Because reductions is one of the most crucial concepts of algorithms. Okay, how to reduce one to the other. Okay.
I mean, all the reductions we did in class, or even the ones we did not do, like the other way.
Even the ones that we did not do, of course.
Oh my God, okay.
I mean, is there something to say that, I mean, you have supposed to try out something by yourself? There were problem shares set has been also been posted, by the way, about this modeling reductions and all. Some more problems that will be uploaded. An assignment will also be created. Okay.
Even some general statements about reductions, like if P1 is polynomial time reducible to P2, then what can we say about the complements and other things you asked? Right? Those things are also will be there in the answer.
Complement.
Yeah. Like what can we say about P1 complement and P2 complement?
Have I asked you those questions?
No. Some questions you asked, right? If P1 is polynomial time reducible to P2, and if P1 is in P or NP, and prove that something
Yes.
is NP here and
Yeah,
then.
yeah. So yeah, those kind of stuff we can ask. The complement becomes a much more complicated question. So I am not going to ask you about the complement. Believe me, the complements are much more complicated objects.
Okay, fine.
Okay, that's why I was a bit worried that you told of complement. Okay, I mean, so let me just, for the heck of your knowledge, there is also a concept of co-NP. What is this class? I'm not going to say it, but basically it's a complement of NP. Okay, it's not the all the problems that are not in NP. No, that is not the case. It is the set of all complements of languages in NP. So maybe if you want to define it, I can just define it for you. This is all the languages such that the language complement is in NP. Okay. And this problem, so that's why I'm not wanting to, so don't worry about this particular definition here. Okay. But just to kind of tell you guys, there is this concept, and that is something, another very important class that is there. And the picture that you might see some point of sometimes is there is this NP, there is this something called this co-NP, and there is a P which is intersection of both. Okay, NP completeness is here. This is NP complete. That's what people believe. Okay, there is nothing, no NP complete problem in co-NP, and this kind of is a starting point of complexity theory. This is called the first hierarchy of first level of the polynomial hierarchy of the classes of functions. Okay. Now, okay. So, any questions that you guys have? Nobody has any questions, any doubts, any curiosity of whatever?
Hello.
Yeah.
Earlier
yeah.
we said that like matching can be reduced to flows. So in terms of this reduction, so how do we show that?
So you tell me, how do we show that?
I mean, like what kind of alphabets we have to take, and we have to give
But
some.
forget the alphabets. You think of it. So don't think about it too much in the direction of the automated theory and all.
Okay.
Okay. So if you want to prove that matchings reduces to flows, right? So you have been given a graph.
So we'll okay.
And you are asked this to and a number case, right?
Yes.
And question is that, does this graph have a matching of size k? Right. And what you do is that you create a flow. What is that flow?
Adding
that flow is basically the, so this is, let's think of it as a bipartite graph for now, okay? Just to say UV. Okay, so this is a U, this is a V. We draw this things. Yes, and we kind of add the stuff here, right? And we have infinite here, maybe, or something like that. Correct? And he asks is that this is the graph. Okay, so this is a G. You produce this another directed graph, which is the G tilde, which is this graph. Now, if G, so you have to prove two things. Okay, so once you prove this one, okay, so this is the G sitting over here. This is S and this is T. Okay, now what you have to prove here? So this is a reduction that we have done. You have given me a graph G, bipartite graph G UVE, and I produce this flow instance here. Okay, so you have to prove me two things. Number one, okay, if G has a matching of greater than or equal to K, then G tilde has an ST path, ST flow of greater than or equal to K. That is one side. The other side is it is the if and only if condition. Okay, by the define if and only condition. If not, I've made a big mistake over here. Yeah, I have told if and only if, right?
If and only if.
Yeah, so it's if and only if, right? This is the important thing.
I mean, image has to.
So that means the opposite is also true. Okay, so they can ask it in different ways, or the other way you can say that if G prime has a matching, has a ST flow of bigger than equal to K, then G has a matching of bigger than equal to K. Now, note that the first one here is very easy to prove. If you guys remember it, this is kind of easy to prove. Why? Because this one you can just say that, okay, there is a matching, so let me just have those flows going along the matching, and that would give me the flow, right? But this one, which is that if you have been given a flow of size bigger than K, you have to use the Ford-Fulkerson method kind of stuff to prove, or to claim at least, that if the graph, if G prime has ST flow of size greater than or equal to K, then G prime also has an integer flow of size greater than or equal to K. And an integer flow of size greater than or equal to K means, what does it mean there? So the integer flow will produce a matching in the graph G. Okay, so you have to prove both the statements.
Yes, sir.
Is this clear?
Yes, sir.
Yeah.
And one more thing, from G to
Yeah.
G prime, that is a polynomial time thing also.
Yes. So why the polynomial time? I have not told you why the polynomial time. Think about it.
Yeah. Fine, sir.
Okay, it's an obvious thing because I have not done anything non-trivial here, right? I've added an S,
Yes.
I have added a T, I have added some weights, right?
Yes.
And I've created this. So it's a polynomial time reduction.
Mm.
Okay. Yeah. So maybe you have to prove that thing also. Yeah. So that is the third thing you have to prove, that G to G prime is a poly time reduction. Now this one, I mean, again, see, this one is kind of obvious for most of the cases. These two are usually the harder ones. Okay, the if and only if thing. Yeah. Okay. Any other questions? Somebody else was going to ask something.
All these things are defined for decision problems. So all the other kinds of problems.
Again,
there
see,
are some-
again, the optimization problems, okay, are every optimization problem can be converted to a decision problem. That's something that we discussed in the last class. Okay, there is something called counting problems. Okay, like how many number of perfect matchings are there in a graph, and so on and so forth. Okay, so they are basically called the how many number of solutions are there. Okay, how many number of solutions, that is how many different witnesses are there basically. Okay, and they kind of come under another class of problems, and you have this class called sharp P. Okay, and then sharp P complete and so on. So I am not going into those things as such, but there are classes that are there. Optimization problems are basically same as decision problems, and then you have the sharp P problems that are counting problems. Yeah.
So all the and other searching kind of problems. So
Right. So
Mhm.
searching kind of problems have not been categorized as such, but you can convert it to one of those problems and try to understand these things about that. I mean, usually when we say, I mean, everything has been defined in the world of the decision problem only. Everything else can be converted to that to some level. So if you think that a particular kind of searching problem is hard to do in polynomial time, what happens, what we usually try to do is that we try to say that, okay, if I can do this problem, then I can solve this NP complete problem. Which means that if I can do this problem, then I can solve this. Then P is equals to NP kind of stuff. right? And so that is how we put it. Now, actually, theoretically, there are some other kind of reductions that can be defined for that, like not just polynomial time, but there's something called Turing reductions and all. Again, these are there. Again, if you go into complexity theory, you can define it accordingly. Yeah, but usually when people talk about this, this is the most common one to be defined. Okay. Yeah. Any questions?
One more question in the definition of NP class.
Yes.
Like, so the prover and the witness and the verifier, right?
Yes.
They have just one interaction, right? The witness.
They have
with
only one interaction.
And
Yes, they have just one interaction.
Like, and with one witness, how do we say that like the problem can be solved in polynomial? Sorry, NP time or not?
You give a proof, right?
Yeah.
I mean, what do you mean by NP
I
time?
might be like,
There is nothing called NP time. Okay. A problem is in NP, meaning if there is you can think of it, there is a small witness.
yeah.
Okay. So like if I ask you that is there a vortex covert of size K, and you said yes, then the verifier gives me the witness, which is the vortex covert. Verifier says, okay, see, here is the vortex covert. Right.
Yes.
Just one time. If I say that, okay, here I give you a SAT, and I say that is this formula insatisfiable? He said yes. Then you give me the note that it is only if there exists a name. Okay. So a language, sorry, L is in NP if and only if, right? For all X in the language. Now, this is something important. Remember that. Okay. There exists. So, okay. So maybe if there exists a algorithm, okay, A, or maybe I could write this one as a verifier, V, okay, a polytime verifier. And for all X, there exists a poly-sized witness, say WX, such that, okay, X is in L if and only if V, okay, X WX equals to 1. Note that this is very important here, that this is only for here. No, this is not only, sorry. Yeah, so maybe I should not have written it right. If X is in L, then there exists a witness such that maybe this is, and V of X is 1. Okay, so maybe this is how I should write it. And if X is not in L, okay, then for all poly-sized witness WX, V of X WX equals to 0. Okay, so basically thing is that if X is not in L, then you should not be able to fool the verifier, irrespective of that. Okay, but if X is in L, then that you should be able to give a small witness and that's it. Right. And that witness is basically a proof. You are claiming that the ILP solution is bigger than 1000. Then you give me an ILP solution. And all I need to do is that verify that that is indeed a solution, and that is indeed giving me something better than bigger than 1000. Right.
Yes.
So that is the concept of interaction.
Yeah, and this definition doesn't say that whether like our witness is a correct algorithm or not, something like that.
Witness, there is no algorithm.
Yeah, no algorithm.
Witness is
Even I can use
witness is an
some
oracle. It's a
oracle.
god. Yeah. So if X is in L, there exists a witness. That's it. Okay. Someone can come up and say it. Okay. I'm not saying that how are you finding the witness? No, of course not. The witness, all I say is that it's a size is polynomial size, and you prove it.
Okay.
Any other questions? Hello?
No, sir, no, sir. That's fine.
Anybody else? Anybody else? Is there anybody else who is there in the class? There seems to be.
Yes, sir.
Okay, you guys have no questions, right? Okay, the one question I was hoping that you guys give me is that, okay, this is something we have talked about. What do you do when you have to solve a problem that is NP complete? And this is the most important question that dictates modern day computer science. See, in this whole course, we have basically dealt with how to solve some very simple questions, right? How to find out whether the shortest path between S and T, how to find the connectivity, how to maybe find a spanning tree, how to maybe multiply two numbers or some kind of stuff like that, right? Sort something and so on. But none of them were NP complete problems. What do you do? What do you think you can do? Can somebody please give me some ideas how to solve them?
Using heuristics.
Right. So this is where things come in. Okay. First one, what one was called heuristics. What is heuristics? Heuristics basically says that, okay, that I will kind of come up with an algorithm. I don't have a proof that the algorithm is correct, but somehow I will run that algorithm on my input and hope that on that input it will give me the correct answer. But if it is NP complete and my algorithm is running in polynomial time, then chances are very unlikely that my algorithm is actually correct. Everybody knows that. But the hope is that the inputs on which I am going to apply my algorithm, from that set of things, they become correct. Okay. Now, this is a very tricky part, and this is where computer science kind of diverges into these two groups of work. One of them is like, see, there are some good heuristics that are there, and some completely hopeless heuristics that are there. Because you can always tinker with an algorithm and make an algorithm work for a particular set of inputs. Right? So either you have to come up with if you come up with an heuristic, you have to give a very good reason why the inputs on which you hope that the algorithm will solve will be solved. Okay, so this is really based on hoping that the algorithm outputs correctly on the inputs of interest. Now, here there are two important things that are there. Okay, number one is hoping. There's a lot of hoping that is done, and there are the things called inputs of interest. So which inputs are interesting to me and which are not? Which inputs are the ones for which I want it to work and which are not? These are very vague terms and they are not necessarily done. Understood. But good that you started with this particular example. Any other way of handling this thing?
Brute force.
Brute force. Brute force is usually very slow. Okay. So using brute force, meaning you just solve it. Okay. So these are usually exponential time. But this only works for small size inputs. So only works for small size inputs. Small inputs. Okay. Any other? Any other? We have kind of talked about another one. Okay. See, note that I have kind of specifically harped on two particular problems all throughout this whole last few weeks. Which are them? They are ILP and SAT. For some reason, two problems have got a lot of importance, and in some sense, for them, there are lots of algorithms that are done, that are there. Okay. Now, okay, of course, they are NP complete, so you don't expect them to have polytime algorithm, but what they have is what is called, they have algorithms which on most inputs, okay, on most inputs or on many inputs, actually outputs correctly. Oh, sorry, for all inputs, it outputs correctly. Okay, so there exist solvers that output correctly using on all inputs. But now this is a big but. On some inputs, they run for exponential time. And on most inputs, they are efficient. Now, this is a very important kind of understanding. Again, here there are two important things, right? There's a big but over here, and the fact that it's the most input, they're good. So important thing is that you are never going to get a wrong input, but maybe your algorithm will keep on running on and on and on and on and will never give an answer. But it is, they have been kind of worked on, and this kind of heuristics in some sense you can think of has been worked to such good level that these two problems particularly have got a lots and lots of attention, and they have outstanding solvers. So the third technique that you can do is reduce to ILP or SAT. Now, which is better? That is something of a big debate. Which is better? Which solver is better? ILP solver or SAT solver, and so on. That depends on the problem. Okay. Any other questions? Any other attempts that in which you can try to solve them? Do you guys have any idea? Nobody has any clue about these things? So for example, I want to solve vertex cover. I have given you a graph and I asked you to basically, question is that I want to find out the smallest vertex cover, right? that is same as we cannot do it in polynomial time because it is NP complete, the vertex cover problem. What can we do instead?
Use some kind of approximation or randomization.
Right. So that's the next thing that you can do. There's something called an approximation. Something like, I don't know how to solve vertex cover, but can I come up with a solution that is close to the optimum algorithm? So this is a, in some sense you can think of, I told you so far that optimization and decision problems are similar, but this is, I'm talking about approximation to optimization problems. Okay. Now this is a big area of research, another huge area of research. Okay. For example, think of it. Okay, I have given a graph. Given a graph G. Okay. Say you don't know. Okay, such that G has a minimum vertex cover of size T. So you don't know this T. You just been given this graph G. Output a vertex cover of G whose size is less than twice. So this is the problem. Think about this problem. So see, I am not asking you to find out the minimum vertex cover. But I'm saying that, okay, find a vertex cover which is twice as worse than the optimum. Can you do it? Okay. And the fact is that this problem can be done in polynomial time. Okay. So I'll let you guys this one. This is a problem. Think. Okay. Now, this can be done. Okay. I am telling you this can be done. And think about it. You can come up with a problem with a polytime algorithm for this. But also we know that this too, okay, if 2 is replaced with 1.99, then not possible. So this, what is written above here, is basically says that the vertex cover can be approximated, too approximated. We know how to do it. You guys can also find it out. This is your exercise. Try to find out. But I'm also saying that anything better than approximation cannot be done. This is another big area of research. This is called inapproximability. Now, this is a very hard research area, but this is a beautiful area. How far you can approximate? I'm just throwing names here, okay? So this is something, again, just like there's an approximation algorithm, there's an inapproximability which kind of goes with it. Just like there's P and NP complete kind of stuff, this is what it is, okay? Now there is another, so this is the fourth attempt, right? There is a fifth one that is called use randomness. Okay, so means output correctly with probability say more than 2/3 or something like that. Okay, now this is another big area. This is called random algorithm, randomized algorithms. This is also used a lot, and this also has this kind of limitations. How much can be done, how much cannot be done, and so on. In fact, most of the modern day learning algorithms are a mixture of approximation algorithms and random algorithms. Then there are other things kind of similar to what was you can expect. It's called the parameterized algorithms. Say, I know that if I given a graph, finding a vertex cover is hard, NP complete, finding the minimum vertex cover. But if I guarantee you that the graph has some other structure, then can you do something? Whether the graph has a small click, does it mean that you can find out vertex cover, minimum vertex cover? If I say the graph has minimum coloring number, then can you say that? So in some sense, you try to identify what all classes of graphs or what all parameters of graphs are causing the problem to become NP complete. Okay, and you work on that direction. So that will kind of classify the problems or instances based on the size of the based on the parameters. So this is called the parameterized algorithms. So these are the 6 most commonly used techniques in this field of algorithms. Okay, and this is something that I want to stop this course with these 6 things. This is the most important thing to kind of remember, that in this course, what we have done, we have tried to understand what an algorithm is, formalize algorithms, come up with some algorithms, some basic algorithms like sorting, searching, some basic graph algorithms, some basic techniques like dynamic programming, divide and conquer, recurrences, and all of this kind of concept that was done in the initial part of this one. Then we have also looked at things like how to reduce problems from one to another and so on. But all of these things that we have done are mostly within the realms of polynomial time. Okay, we end this course by saying that there are problems, or most of the problems that are interesting enough, or honestly speaking, that are interesting, are problems that are NP complete, for which we don't expect to come up with polytime algorithms. Okay, and if you ever take the advanced algorithms course or the complexity course and all, these are the things that you will look into. That, okay, now that we have understand algorithms and we understand that this is the area, this is set of problems that are NP complete, how do I solve it? Of course, there are problems which are beyond NP complete, meaning they are beyond NP. There are problems that are much harder in exponential time and so on and so forth. Those are also studied, but usually we get stuck at this NP complete problems only. There is also other class of problems that somebody asked, the sharp P and all those things, which also are sometimes looked into. So these are the 6 techniques that are there. Again, as if you are from the theoretical bent of mind, there are algorithms which are the things that are interesting are this. So brute force is actually interesting. This is also something sometimes called the exact algorithm. And there the idea is that come up with the best exponential thing, like 2 to the power n or 2 to the power n by 100, that matters. Okay, kind of stuff. So this exact algorithm, okay, approximation algorithms, randomized algorithms, and parameterized algorithms. So these are the 4 problems where if you are into theoretical research, theoretical bent of mind, these are the ones to go for. If you are coming from a more of an implementation or applied kind of bent of mind, then either the heuristics and that's always comes with a pinch of salt, or using reductions or solvers are the two ways to go. In fact, this area of research, something that I have recently got very interested in, and a lot more work is been going on in a way to kind of replace many of these heuristic kind of techniques to this kind of solver kind of technique. The solvers are not wrong, they are just slow, whereas heuristics can be wrong. So using this understanding, replacing many heuristic algorithms to reducing to solvers and then working on that. I've been working on that also. So anyway, so I think I have given you a lot of stuff for the last class. There will be a problem set that will be uploaded on reductions, and there will be an assignment that will put up. And next week or next Tuesday, as somebody asked, I will try to go a little bit over the Fibonacci heaps. It is not a part of the course. Okay, it is not a part of the syllabus that will be there. It's just for people who are interested in understanding more. If you guys want to know something more about some particular topic, I'll be happy to give lectures on any of them. Okay, yeah. So this, and if you had doubt with any of this stuff, please ask questions to us or TAs or anyone. There will be the NSEM, and you guys have to tell me when the NSEM will take place. So, okay. So, any questions?
Sir?
Yeah.
Syllabus for NSEM is, I mean, whatever we have studied from the beginning, right?
Yes, whatever we have studied from the beginning.
Okay, sir.
Quantum algorithms are also will be a part of, I mean, I think will be a part of this,
quantum algorithms. So there is also this concept of quantum algorithms. Let me know. Yeah, you can write this one also. So there is this concept of quantum algorithms also, but that's again a completely different world altogether it goes into. There is this thing called quantum algorithms. But quantum algorithms is like a, yeah. Actually, quantum algorithms doesn't help us solve NP complete problems, I must say. Not that we know of. It helps us to solve many problems which are in NP, but not in NP complete, and come up with better algorithms in polynomial in terms of polynomial time. But NP complete problems are not solvable in quantum using quantum algorithms. So, yeah.
Sir?
Yeah.
Like in the end sem, like the portions covered before mid sem, like what,
yeah,
what percent of them will come on? Like, can you
100?
Sorry,
you can assume that every part that has been covered, 100% will come from there.
I mean, it will come by the.
I mean, I'm not. I have not made the paper, and I'm not going to think about it also.
Okay.
So you mean to say that you will know how to solve a problem, but not know how to sort? Is that what you are saying?
How to solve the problem, but
solve some problem, but you don't know how to sort a array. Is it?
No. I mean, since some of the portions are already covered in the mid-sem, so that's very paper might be thick.
I don't understand what do you mean by this kind of statement, I must say.
I mean, paper might be quite heavy, right? For the
yeah, paper is heavy.
Okay.
Yeah. Algorithms is a hard paper. But again, as I tell you, if you follow this set of things that have been done in the class and you have been following the problem sets and the assignments and all, you should not be hurt. Okay. Yeah.
Sir, for P and NP and SAT related problems,
yeah,
requirement is enough, right?
Yeah, Corman is good enough.
Okay, sir.
Corman is very good.
Okay.
Yeah. Okay, any other questions? Hello. Okay, so I'm assuming that there is no other questions, and so I will close the lecture today. Okay, bye.
Thank you, sir.